Hello, everyone. I'm honored to have been invited to speak at this chapter meeting. It's been several years since I've been able to attend in person. The title of this presentation is These Are Our Needs, Make It Happen. I'll go into more detail exactly what that means. First, I want to talk a little bit about the International Council of System Engineering Requirement Working Group. Requirement Working Group, I'm a co-chair and a past chair, and I've been involved in it for over 22 years. What it's really about is understanding how to improve the practice of system engineering or product development through excellence in needs and requirements development and management across the life cycle, learning from experiences and sharing that with the system engineering community. And by experiences, we're really talking about lessons learned, both good and bad, which turn into best practices. And then we want to communicate those best practices to the community. And we also question approaches that yield poor outcomes, especially questioning some old, outdated approaches to product development that seem to work for 20th century, but maybe are not as applicable to today's more complex software intensive systems operating in more complex operating environments. And then we publish this guidance and continue to do research in requirements development management, including the understanding of needs, requirements, verification, validation. The chair is Tammy Katz from Ball Aerospace. Like I said, I'm co-chair. I have my own consulting company. I'm semi-retired, but I do have several clients that I'm supporting. Mike Ryan, Capability Associates from Australia. He's semi-retired, but still doing a lot of training and consulting for different clients. And then Raymond Wolfgang from Sandia National Lab. Currently, we have about 408 members, one of the COSI's largest working group. I think it's the second largest working group. But we have members from industry and academia with the common purpose of improving the practice of system engineering through improvement in needs and requirements, development, management across the system lifecycle. We have several products that we're putting out. And COSI has a system engineering handbook, which we provide inputs to. We're also providing inputs into the system engineering book of knowledge. Products that we've developed on the left is our COSI Requirement Working Group white paper, Integrated Days of Foundation System Engineering. It addresses model-based system engineering, moving from a document-centric to a data-centric practice of system engineering. We've developed a needs and requirements manual. Then it's supported by the guide to needs and requirements, which is a condensed step-by-step version with some additional examples on defining needs and requirements. And then we have a guide to verification validation, which expands on some of the material in the needs and requirements manual concerning verification validation across the life cycle. We have a guide to writing requirements that's been around for 4 or 5 years or maybe longer. We just updated it so that it's all in line with all the other products. And there's several different working groups came to us that they're going to develop their own guides that are domain specific, like safety, security, system of systems. The needs and requirements manual is our main manual that we have, 457, 60 pages. And it talks about some basic concepts up front. Then it goes into elicitation of needs, maturing lifecycle concepts and the needs, transforming those into requirements, and then talking about verification validation across the lifecycle. Has a lot of guidance in customer supplier arrangements. Needs and requirements manual has a lot of lessons learned. It addresses some ambiguity that exists in certain standards, and it's kind of down to earth, helps practitioners actually practice system engineering and product development activities. It's a good resource to go to when you have questions about specific aspects of needs and requirements. Like I said, it's supported by these other guides. They're all released in May and are very much in alignment with each other in terms of concepts and terminology that's used. There's a summary sheet that has a summary of a lot of the information in 6 pages, and there's a link that you can click and go to that on my Dropbox page. We have a lot of events throughout the year, and anyone that wants to attend can. We do this all by Zoom. Our membership is around the world, and Zoom really has enabled us to do a lot of things that were more difficult to do in the past. And so every month, the requirement working group has some kind of event that we make available. A guest speaker that gives a presentation, needs, requirements, first case validation topics, different tools that are being developed. Or we have the concept of exchange cafes, where it's like a lot of like-minded people would get together at a restaurant or cafe and have a discussion about a given topic. We usually have some kind of a main topic, and then it's just kind of an open discussion, like if a bunch of people were in a cafe sitting around a table having a conversation about some topic. And this allows our members to contribute ideas toward these topics, and they're encouraged to share their experiences and questions with a broader working group community. All of these are recorded and put on the YouTube channel that we have. Upcoming events that we have, just last week we had a presentation by Beth Wilson concerning the system of systems and challenges associated with that when it comes to defining needs and requirements and verification validation. I think a lot of you are probably involved in the system of systems in some way. In August, she's going to come back and she's going to lead a discussion on system practitioners and how they could use what's in our products in defining the system systems. And then we have, various other topics throughout the year. Anyone can attend these sessions. If you're interested, let me know, and I'll make sure to send you a link to any of these sessions. Everything we do, we put on the INCOSE RWG YouTube channel. For an expansion on what I'm talking about tonight, if you just go to YouTube and search INCOSE RWG, you'll see we have probably 20 or 30 presentation videos that we've done over the last 2 years on different topics, and they're available to anybody. You don't have to be a member of INCOSE. If you're interested in a given topic, you can listen to those presentations. Several organizations are using those as like lunch and learns, play a certain presentation that they found interesting to other workers, and then have a discussion about those topics later. Some key basics before I get into the main part of the presentation. One of the things that in our products is that we try not to focus just on systems engineering when we talk about product development or developing system. We take a more broader view that instead of saying the system engineering team does something, we say the project team. We feel that project management and system engineering, when it comes to product development, are just two sides of the same coin. And so you should have a core team that has a project manager, lead systems engineer, supported by a project management integration working group or the system engineering integration working group. And they're supported by subject matter experts. And then they tap into different lifecycle stage support personnel when needed. And the result is that we have integrated multidiscipline collaborative project teams, try to minimize the silos. And so the teams have people from project management and system engineering as well that focus on specific areas, activities involved in either project management or system engineering. And one of the problems is when we have a supplier, we contract out. One of the challenges is how to engage the supplier, that contractor, in this integrated, multidisciplined collaborative team. And so that's something to think about when you're doing your project management planning. The title of this is, These Are Our Needs, Make It Happen. I'm going to talk about needs and requirements. So notice I didn't say I'm starting the project out with these are the requirements. I'm starting out saying these are our needs. And then I'm asking the team to go make it happen. And so there's a whole bunch of work they need to do as part of that. So at the beginning of the project, rather than asking what are the requirements, we should be asking what are the needs. And I'll go into the difference in just a second. And before defining a set of needs, we must first define and understand what the stakeholders need. There's a whole reason for your project is that there's some problem that needs to be addressed, and there's various stakeholders that are involved in that, and they all have their needs. So we should understand that before we attempt to develop a set of requirements. But both the needs and requirements must be defined, but it's both needs and requirements, not just requirements. Because needs and requirements are the common threads that tie all product development lifecycle activities and artifacts together. So when you look at an overview of the whole lifecycle, the key thing that we're talking about tonight is developing an integrated set of needs that then will be transformed into a set of design input requirements, then is transformed into an architecture and design, transformed into design output specifications that you're going to build or code something to, which results in a product or a system of interest. The term design inputs and design outputs is useful. It actually comes from the medical device world, and the terms are codified in Title 21, Part 820 of our law under the FDA on developing medical devices and pharmaceuticals. So we've adapted this term about design inputs, design outputs, design input requirements, and so on from the medical device world. So when we talk about needs versus requirements, needs represent the stakeholder, customer, acquirer view of the product to be developed. And what they're doing is they're viewing the product from a closed system standpoint, or some people refer to as a black box. If you pick up your phone and you go and look at the phone, what can you see? And then how do you interact with the phone? That's the stakeholder's view. You have no idea what's going on inside. You have no idea what actually the software inside's doing. And frankly, you don't really care as long as that phone does what you need it to do. When I say needs, does it have the functionality? Does it have the characteristics, the features that you need? Does it have the performance you need? Accuracy of the data, the amount of storage and stuff. You have needs concerning quality and other utility type things. You have needs with how it interacts with external systems and actually interacts with you, the user interface. There's also standards and regulations that from a stakeholder standpoint, you expect that product to adhere to, especially safety, security. So that's the stakeholder view, and that's how we want to communicate that in a set of needs. Ultimately, it's the needs that developers of a product have to meet. So the needs ask, what do the stakeholders need the product to do that will result in their problem to be solved or opportunity to be realized within defined constraints? They communicate the stakeholder expectations for the end state once the product is built and delivered. In the end, what will make the customer happy? When it comes to validation, we're going to validate the product or the system against this integrated set of needs. Needs are not requirement statements. The need statements do not include the word shall. Unfortunately, in some domains, people talk about stakeholder needs and requirements as if they're one thing, and they tend to communicate those as shall statements. So you see a stakeholder requirements document, there really should be a stakeholder needs document and not have the shall statement. The shall statement should be in the design input requirements. Examples, the stakeholders need the system to do something. The stakeholders would like the system to do something for a goal. Rather than saying the users shall be able to do something, you could say the users need to be able to do something, or the stakeholders need the system to allow the users to do something, and that's acceptable for a need statement. But the users shall be able to is a lousy requirement. It doesn't have the characteristics of a well-written requirement. It's written on the users. It's in passive voice. It's ambiguous. It's a really bad requirement. But as a need statement, it communicates an expectation of the stakeholders. Rather than say the system shall meet applicable government safety standards with the shall, again, that's a lousy requirement because who decides what's applicable? It's very ambiguous and you really can't verify against it. But to have a need statement where the stakeholders need the system to meet applicable safety standards and regulations, that's okay. The ambiguity is going to be taken out when that's transformed into a set of well-formed requirements. So using these distinct formats helps make a clear distinction between needs and design input requirements. Now we're going to flip to a totally different perspective, and requirements, what we refer to in our products as design input requirements, represent the technical developer view of the product. So you do an engineering assessment. What must the product do in order to meet the needs? The needs are transformed then into the design input requirements that will result in a design that when you build a system to it, those needs will be met. And it's the design input requirements that we verify the product against. With this view, the quality of the requirements is dependent upon the quality of the needs once they're transformed. So if our needs are poorly formed, they're ambiguous, so we really don't know what the intent is, they're incomplete, they're inconsistent, they're not feasible, then the requirements are going to have the same defects. And so we need to spend time up front making sure that we have a good set of needs first and get agreement on those. And a lot of you would call that defining the scope, baselining the scope to understand what the needs are. Then it's that baseline scope then that we develop the requirements in order to realize that scope. Requirement statements include the word shall, an example of transform and need into design input requirements. For the example I gave, the users need to be able to do something, or the stakeholders need the system to allow users to do something. Then the project team would do this engineering analysis and determine what the system must do such that the users will have the capability to do that action. Based on that analysis, they would write one or more design input requirements, shell statements, that when implemented would result in the user being able to do that action. And those requirements need to have the characteristics of well-formed requirements according to a given set of rules. So they're written in a very structured, natural language with a template. And that's what our guide to writing requirements is all about. How to really formulate well-formed needs or well-formed requirements or sets of requirements. And so project success really depends on the project team first understanding what's the source of concern, the problem or opportunity or threat, develop a mission statement of what the project's all about, what's its purpose, what are your high-level goals and objectives, what measures are you going to use to determine success, what constitutes acceptability or desirability of a solution, the what is necessary for acceptance. Again, I said what makes the customer happy. From a contract standpoint or developer standpoint, we really need to have documented exactly what is necessary for acceptance. If we meet that necessary for acceptance, our product will be accepted. Necessary for acceptance may be defined by a customer, but like in the case of a medical device, it's defined by the FDA. And so we need to understand just what is that necessary for acceptance. And we also need to understand the conditions in which your system of interest, your product must operate. What's the operating environment? That's why I said about system of systems. Any system is going to have to interact with what I call the outside world or the macro system it's part. And so what are all those interactions? Those interactions defined in terms of interfaces. So we need to understand what that is. We also need to understand the user interactions, the operator, the installers, the maintainers. What are their interactions with your system also? Together, that defines an operating environment, along with the natural things that we think about as in an environment. And so this knowledge allows us to develop concepts you do as part of planning to be defined, analyzed, and matured, and a formal integrated set of needs defined, agreed to, and baseline. But when we're looking at the concepts, we don't want to just focus on the product. How are we going to manage the project? What is their schedule and budget? What are we going to be doing in-house? What are we going to outsource to a supplier? And so we need to understand all that, what different organizations there are, all the standard project management things that need to be determined as part of this upfront work. And then from a product development standpoint, how are we actually going to engineer the system? If it's software, maybe we're going to do it through some kind of an agile approach. If it's a hybrid system, hardware, software, maybe we're going to follow a more traditional system engineering approach. How are we going to store our data, manage our data? We're going to do this the old-fashioned document-centric way. We're going to do this from a data-centric way. What's the team going to be? A lot of things that we need to consider. And then the product lifecycle concepts. So we have to think about our product and what are the different life cycles it's going to go through. Each of the life cycles can result in the different sets of requirements. So we need to develop all that. And another thing, as far as our life cycle concept goes, we need to think about upfront architecture, both a functional architecture and a physical architecture, because one of the big problems we have in scope definition from a technical standpoint is technical maturity. Is what we're asking for even feasible? But we can't answer that question if we don't start looking at technology, and we really can't look at technology unless we start thinking ahead into some design options. And then when we have our critical technologies defined, then we have to determine what their maturity is and whether it's feasible to even think about using that technology in this particular product. And so there's a lot of work to be done before developing a set of design input requirements to which the system is going to be designed and built and coded. And a primary reason for project failure is the failure to recognize the need for and doing this upfront work. When I talk about upfront work, start with stakeholders. Stakeholders have the problem or opportunity. We assess what that is. We define what the desired outcome is, define the mission statement, our goals and objectives, define measures, Then we interact with the stakeholders and we want to figure out what are their real world expectations, what are their needs, what are their requirements. We need to go and assess the risk. And from a risk standpoint, it's project management risk, product development risk, or technology risk, operations risk, what could go wrong if someone's using the system, a manufacturing risk. We need to look at risk in a whole bunch of different ways. In some cases, the way we're going to mitigate that risk may be through how we build the product. So that's going to have to be reflected in our needs and in our requirements. There are probably higher level needs coming from management, higher level concepts and requirements that came from management. These are all constraints. I talked about the operating environment that contains a bunch of existing systems. And so those existing systems, how we interact with those, especially if they're already existing, could constrain what our solution space is, cost and schedule naturally. And then I talked about technology from a feasibility standpoint. And so we go through lifecycle analysis, maturation. And in COSI, that's where they're really leveraging on the availability of modeling tools that people can use now to develop functional behavior models and different kinds of models of the system early in the life cycle. That gives you the underlying analysis from which to define the integrated set of needs that we get through the needs analysis. And then that's transformed through requirements analysis, then into our design input requirements. Traceability is critical to managing all these relationships. And that's why a data-centric practice of product development, system engineering is so important, because if all this data across the life cycle is in a data information model that represents both your system of interest, your product, and the artifacts of the project management and system engineering, then you have a single source of truth. And with it linked together, when change happens, it makes it much easier for you to do a change impact analysis. That's one reason why people are moving toward this data-centric practice of system engineering or product development. The last topic that goes with this is validation across the life cycle. A lot of people think about validation as something we do at the end of the project. We don't take that view. We say validation should not be thought of as something done at the end of the project. Validation should be done across the system lifecycle. So when we define a set of needs, we got to validate that really addresses the stakeholder real world expectations. We develop a set of design input requirements. We got to validate that represents the needs. And the same with the architecture, design output specifications, and then our realized product. So we're doing validation as a continuous activity across the life cycle. And early validation, the earlier we're doing this validation, helps decrease issues when the product is delivered or put into market. The result is by doing the early validation, it helps us avoid having a whole lot of unpleasant surprises at the end of the project that then we have a lot of rework that really impacts our budget and schedule. So by doing validation across the life cycle, especially the early stuff, can actually help shorten the time to market and help reduce schedule slips and budget overruns. So this is one of our main products that we developed. It's very popular, and there's a link to it. In one place, it talks about verification and validation in context. It talks about the whole life cycle. Organizations are printing this out, putting it on their walls, putting their bulletin boards. A lot of discussions result from viewing this. It starts on the left with stakeholder real world expectations. We do our life cycle concepts and needs definition, resulting in the integrated set of needs. We validate those needs against the stakeholder real world expectations. They're transformed into a set of design input requirements, which are then validated against the needs. And then those transformed in architecture and design, resulting in design output specifications that we're going to go and code and build to. Again, those are validated against the needs, because we're always asking the question, are we building the right thing? Do we have the right design? And when we build the system, we're going to validate against the needs. Do we actually build the right thing? And then we have verification, where now we're verifying against the requirements. The needs and requirements we verify against the organizational requirement definition requirements, the guide to writing requirements, or an in-house work instructions that you have that talk about how to formulate needs and requirements, following the rules. That would be a needs verification or requirements verification. Our design output specifications, we need to verify that that design actually implements the design input requirements. From a realized system of interest, we need to verify from a production standpoint through manufacturing, did we really build it right? Did we build it spec? And that's generally a quality function within the organization. But also we want to verify and make sure that that realized system actually met its design input requirements. On the bottom, the design controls, these are all your in-house work instructions, procedures. They really apply to the people doing these transformations. So every place you see a transformation, that should be documented how that's going to be done within the organization. Now, once we have the system developed, we've added on here the operational system, maintain system, dispose system. We're going to do post-development validation. And this is a continuous activity after the system has been delivered. Do we still have the right system? Things change over time. The stakeholder real world expectations and needs change over time. So there might be a time where our system's no longer able to meet the needs and it's time to go and develop a new product or system. On the same token, we want to do post-development verification. Systems degrade over time. So we need to be monitoring the system to see, does it still meet its requirements? If it's not, then what do we have to do to fix that system so it still is meeting its requirements? It also shows on here integration. Again, integration isn't something you do at the end of the life cycle. Integration is something that we're doing from the very beginning of the project. We always want to be managing the integrated system. What are all the interactions of the parts? We have to take this holistic view because the behavior of a system is a function of the interaction of the parts. When you actually build a system and put all it together and you start doing system validation in the operational environment, you're going to find that there's sometimes emerging properties that weren't really part of your needs and requirements definition, but these properties came up. Some are good, some are bad. So we need to be looking out for those across the life cycle. Again, you can see where validation and verification are continuous. The earlier we find a problem, the better it is. The cost increases almost exponentially the later in the life cycle we go before we identify a problem and have to fix it. So product validation, we have an increased focus on that. One of the classic definitions of product validation is validating that the realized physical integrated product meets its intended purpose or use and identify and assess its behavior and emerging properties, like I was saying. In its actual operating environment when operated by its actual intended users. And that's where classic product validation ends. But in today's world, that's not sufficient. So we've added another part and does not enable unintended users to negatively impact the intended use of the system, nor allow unintended users to use the system in an unintended way. This is really, really important. And by putting this in the definition, this is going to force people up front when they're defining needs to actually have needs concerning these bad things. And by having needs, then you're going to have a set of requirements that are going to be implemented to prevent this. And you're going to build a system that actually can pass this product validation. So when you talk about product validation, you have to ask yourself, what's more important? Product verification or product validation? You know, project success is really based on the product passing product validation. So passing product verification, but failing product validation results in a failed project. So this says is that even though proven that you've met all the requirements, you could still have developed the wrong system. If the requirements are defective, incomplete, inconsistent, whatever the problems are, that could result in a system that was delivered that met those requirements, but it still was not the right system. And so what are you going to validate the product against? And we're saying the integrated set of needs. So where are they defined? And so you need to have a plan for where you're going to actually document the needs, maintain them, configuration control them. Who's responsible for defining the needs? In the end, what's necessary for acceptance? So for final acceptance of that product, what has to be proven to the acceptance authority? And this all must be made very clear in customer supplier agreements. I want to go back real quick to this figure. So I said that design validation should be done continuously. So if you issue a contract to a contractor and one, you haven't done the upfront analysis and you haven't defined an integrated set of needs, then there's nothing to validate against. So you can go through and develop this whole product and you can do verification, but without having anything to validate against, you could be wasting a whole lot of time and be developing the wrong system. And so these are our needs, make it happen. And the expectation is the developer understands what the needs are. The customer has went through that early analysis to define the needs, underlying analysis and needs available to the vendor up front so that this continuous validation can take place. So when we say make it happen, we're telling the project team, you got to do all that upfront work. You got to have a well-formed set of needs and then transform those into a well-formed set of design input requirements. That's the end of the presentation. We have time for the question and discussions.
All right, Lou, thanks. That very busy graphic that shows the integrated loops. The more I look at that, the more I'm thinking this is going to take some time to digest, and I think it's going to be worth it. Who has questions?
I understand your use of need and shall. You use should in any of your statements. It comes up in some of mine occasionally.
Shall, should, and will are common terms that you see in your set of requirements. The shoulds are goals, and how you treat the goals is going to be defined in the contract or by the organization. From a needs standpoint, instead of saying should, just say the stakeholders would like, rather than they need the system to do something, they can say would like. And you could use other terminology too. If a need statement is something that's really needed, that's going to be transformed into a shall statement. If there's a need that says would like, that could be turned into a should statement in the set of requirements.
Thank you.
All right, who else has questions? I have one quick one. Seems like this is a whole lot of paperwork to verify and validate the allocations and the needs and then the requirements. Is there any pushback from senior management about being able to pay for it?
So what's necessary for acceptance? From a requirement standpoint, verifying the system meets requirements is providing objective evidence that the system meets those requirements. And so that objective evidence has to be documented someplace. Now, when you say a lot of paperwork, that can be a problem in a document-centric world. All that has to be put into documents, and you spend so much time managing the documents. Just from a configuration management standpoint, it's costly. But in a data-centric world, a lot of that stuff is done incrementally through the life cycle. When I define my needs for each need, I would actually define at that time the validation criteria for each individual need, and that would be in the database. And then the same when I define requirements, I think ahead how I'm going to verify the requirements were met. If you're a customer and you ask a contractor, I want you to build something per my requirements, don't you expect objective evidence to show that your requirements were met? Or do you care? It's kind of up to you. It is unfortunate some organizations don't pay much attention to system verification, system validation. I ask people how much of their budget should they allocate toward system verification, system validation. And I hear some organizations say, oh, just 20%. And I say, well, you failed. In reality, if you really want to show the requirements have been met and the needs have been met, it does take time and effort. It could be up to 50% of your overall development budget to do that. I know I supported a facility modification project once on Johnson Space Center. I was brought in from a system engineering standpoint, and the facility people really didn't have any system engineering background. And so they were used to just building something and then having a checklist to go through and making sure, yeah, it was painted right and it has bolts where it's supposed to and whatever. They didn't really understand verification, especially from a functionality performance standpoint. So it wasn't in their budget, and that created a lot of problems. So the government had to go back and get a whole lot more money so they could prove that the requirements were met and the needs were met. Concerning the amount of documentation and possible cost associated with doing verification and validation across the life cycle, The whole concept of doing it across the life cycle as continuous processes is for the development team never to lose sight what they're trying to develop, why they're trying to develop. And so from a validation standpoint, no matter what we do, we should always be asking ourselves the question, are we developing the right thing? Is what we're doing going to result in meeting the stakeholder needs? While system verification, system validation that occurs toward the end of the life cycle is fairly formal, requires a lot of documentation. The continuous verification validation is less formal. And so when we are going to baseline a set of requirements, we ask the reviewers to review the requirements. And one, from a validation standpoint, we're asking them, do the requirements, if implemented, communicate what needs to be done in order for your needs to be met? And then also from a verification standpoint, we're asking them, are the requirements formulated properly per the rules for writing good requirements? Do they have the characteristics of well-formed requirements according to your organization's standard for writing requirements? Or you can use the MCOSI guide to writing requirements to verify that the set of requirements meets those. And that's just part of the process of baselining set of requirements. Now, once that's been done and the design team now is going to implement those requirements, you would think that they would always want to make sure that the design they're coming up with will result in the requirements being met, which is design verification. But also they should always be asking themselves, is our design going to result in a system that will meet the needs of the stakeholders, which then would be design validation. Once the design is completed, communicated via a set of design output specifications, and the system is built, then as defined in the PMI documentation, then the quality organization is going to want to make sure that the system is built, their product is built to spec. And so does it meet those design output specifications? Once the system's built initially for a new run or something, then we have system verification, which is then verifying that the system actually met the design input requirements, and then system validation that the resulting integrated system will meet the stakeholder needs in the operating environment when operated by the intended users. That's a more formal process. Now, we recognize that that could be quite expensive if you do all the different levels of needs and requirements for all the different parts of the architecture. That could be a significant part of your development budget, maybe 50%, even maybe more. So if the customer doesn't want to pay for that, or the vendor has a problem with that, then there are strategies to reduce the cost. Like one is maybe keep it informal for the lower levels of the architecture, and then focus on more formal verification, system validation at the higher levels of the architecture, with the idea that if we can show that the integrated system meets its requirements, then by definition, the lower level components in the architecture should be assumed that they met their requirements as well. The same with system validation. If it passes system validation, then you'd assume that the lower parts then are also validated to meet their individual needs. Another approach is focus on the needs and requirements that are critical, those that are high priority, those that are safety related, security related, those that are addressing a key risk. Maybe you want to focus on those, and then not spend as much money on the others. So it's kind of a risk-based approach. In the end, it's all about when you're going to deliver the system, what objective evidence does the customer want you to provide concerning whether or not you met their requirements and whether you met the needs. Now, in some acquisition, the only thing that was provided was the requirements. So you got to prove that you've met the requirements per the contract. And the customer is going to take responsibility for the system validation. But I think a good contractor would always be concerned, are we really delivering the right thing? We could meet the requirements, but still have built and delivered the wrong thing that does not meet the stakeholder needs. And so that's what we want to avoid. But again, in the end, what is necessary for acceptance?
All right, Lou, thank you very much for giving us this talk.